So today we're gonna have your attention, please. Thank you. Today we're gonna continue on from where we left off. And originally I was gonna do the proof for the variance for the geometric distribution, but I thought I'd hold off on that until Tuesday. Certainly I couldn't if I wanted to today because of issues with the pen and the mirroring to my laptop. So we'll just do stuff on the board. The reading by the 31st of October, please make sure you're staying up with the reading. Section 3.4 on discrete distributions in the Barron text. It's only 10 pages, but it is fairly terse. It's not a ton of reading, but it will certainly require your attention. So we have everyone. All right. So where we left off last time, we talked about the summary statistics for the geometric distribution, and it's called the geometric distribution because of its derivation and relationship to the geometric sequence. And we showed what that geometric sequence was in its general form, and then we made use of that for our scenario of a series of Bernoulli trials, all of which are failures that end in a singular success. And the scenario we used was the interview problem, where we have a bunch of candidates waiting in the lobby to interview for a position, and we stop interviewing when someone is hired. And so we use that to derive an expression for the probability of this so-called geometric sequence, and that is the probability that we will have a number of failures and hire the X candidate in line. So this is our probability, so-called mass function, and it's called a mass function because it describes the probability or probability mass associated with each outcome of random variable, where a random variable, in the case of a geometric distribution, traffics in the position in line. Are you the X candidate that has that singular success, i.e. is higher? And so we use that to derive an expression for the expectation. And we had this unfortunate notation that's in the book, where they take the geometric sequence, they compute the first derivative of it, and use that result to derive the expectation. And so in similar fashion, the variance requires the second derivative, but we're going to hold off on that for today and hope that all the technical bits for display work on Tuesday and do that derivation for variance, because that's going to on Tuesday, because that's going to require some other machinery that we'll talk about on Tuesday. Okay, so let's go off to the next thing, and I'm going to start off with a little bit of a challenge, and we're going to play a game, and this is going to be a game of chance. And the good news is that I can promise you, if you play this game, that you're going to win something, right? Now, we're not actually going to play it because I don't want to spend my resources to do this. So we're going to have a series of rounds, right? So it's going to be a first round, a second round, third round, so forth, and we're going to keep playing. And each round is independent of the other, right? Meaning that you're going to take the same action or run the same trial or experiment, and you're going to wager something. So you're going to wager some amount, and let's say call that X, and X is going to be a dollar amount. And so I can guarantee you with this game that you're going to win some prescribed amount, right? Every time. But there's a little bit of a catch to it. And so you can wager some amount, and then I'm going to flip a coin, and you can either win what you wagered, great, you get some money, or you can lose on each trial over which you play. And so the caveat is, of course, you're going to keep playing this, and you're going to play it until you win. But I can devise a scheme so that you can always win in this game. So it doesn't matter how hard it is to guess the right outcome. And suppose for this coin, I could make an unfair coin so that the probability of tails could be 90%, could be 95%, right? And you're trying to guess what the outcome is. I can manipulate the outcome, and whether you choose to guess heads or tails, or you keep flipping the coin until you get a heads, I can make this as hard as possible, but still guarantee by the semantics of the game that you're going to win a prescribed amount. Okay, do you believe me? Is that possible? Yes, it is possible. Okay, so let's start out and this guarantee that you will profit. And here's the algorithm for the game. So first you decide how much profit you want to win, how much you want to make. And let's say for the sake of round numbers, easy to work with, you say, well, I want to win $100. Okay. And so the important part with this game is that you're going to stop once you win. So you start out on the first round and you're going to wager your $100. So you're going to bet. And so after you plunk down your $100, I'm going to flip a coin. And before I flip a coin, you're going to guess what the outcome of that stochastic event might be. If you win, meaning that if your guess coincides with the outcome of the coin flip, you stop playing and you go away with your $100. Great. But the interesting part is what happens if you don't win. So if you don't win, of course, the house takes your $100 and you're down $100. You're out $100. You just lose that money. Mathematically, you can describe that as negative 100. Okay. So if you lose, you do the following. Now you double your wager. You increase it from $100 now to $200. And each time you lose, you're going to keep doubling. So it's going to go from 100 to 200. If you lose again, 200 to 400, 400 to 800, 800, 1600, and so forth. So you lose after that first round, and you don't collect 100, you lose 100, so you double your wager to $200. So now you bet your new wager, $200, that's step 5, and then we go back to step 3, right? So you now bet your new wager, $200, you guess the outcome of a coin, and I flip the coin. And that's what happens when you go back to step 3. You determine if your guess was correct relative to the observation for the outcome of the coin. If you win, you stop. But then if you lose again, well, now you're out another $200. So the first round you lost 100, second round you lost 200. So now you're going to double your wager again to 400. And you keep proceeding in this game each time you lose, doubling your wager, and then once you win, you stop. When the game stops, you're guaranteed to have a net profit of $100. Do you believe me? So let's try this out. So who wants to try, right? So we're going to have somebody participate here, right? So you look like you want to flip a coin. Okay, so who wants to bet? We're not going to bet real money. Yes, so Curtis, all right? So how much do you want to win? $200. So Curtis is going to start with a wager of $200. So let's mark this on the board, and we're going to have Sia flip the coin. So round 1, oops, no pen works today. Gosh, it's like nothing works here. See if I have an extra pen in my pocket. There we go. All right, let me do that. So let's have the round, right? And here's the total. Here's the winnings. And we're going to add that up. So round 1. Okay, so Curtis is going to bet. You said 200? All right, so let's have Sia flip the coin. If you could please flip the coin. And what are you going to guess? Heads. Tails. Oh, Curtis loses. All right, so Curtis is down $200. So that means round 1, it's minus 200. Okay, so by the game, you want to keep playing? You said you want to win. Okay, great. I thought I'd get to keep your 200. So, all right, second round, you now 400, right? So let's have Curtis guess. What are you going to guess? Heads? Okay, let's have see if you could please do the honors. Heads. There we go. I want to go to your casino. All right, thank you. So 400, it's heads. You're correct, and you now get 400 for that round, right? So, um, thank you. So you're up, right? You lost 200 here. You got 400, so you net 200, right? So you're always going to win in this scheme. Let's say if we played a third one, right? Let me grab back my coin. It took me a long time to make that. Thank you. Um, let's say you lost in the second round, right? And you played in the third round. That would be an $800 wager. And let's say you lost in that third round and you went to a fourth round, that'd be $1,600. And let's say you won in that fourth round. So if we add all these up, 2 and 4 is 6, 6 and 8 is what? I'm brain farting. It's 1,400. 1,600 minus 1,400. Guess what? You're up $200, right? And so the interesting part about this is that over time, as you get more and more into the number of rounds, it kind of gets serious, right? So your wagering is doubling. But if you're willing to take on that risk, you're guaranteed that at some point, if you win, and let's assume you keep playing until you win, you're going to be up some amount of money. Now, before I give away part of the interesting part about this problem, let's just continue on. Does that make sense? So yes, absolutely, you can design such a game. Now, it would stink if you're the casino because that means you're always going to be paying out money and you're not going to make any money. Okay. So this scheme or this algorithm guarantees that you're going to be up some amount of money, and that amount of money at which you're up is prescribed, right? Okay. So let me ask you a few shaping questions. What type of distribution describes a single round? Well, let's look at the characteristics of a single round. So you have a success or a failure. Either your guess is correct or it's incorrect, and you have these independent rounds, right? So what might that be? Something we've talked about. What do you think? A binomial, not quite binomials related, the Bernoulli, success or failure. A binomial is a set of Bernoullis together, okay? So we have independent rounds, success or failures. And let me ask you another question. So you're playing a number of rounds, and if you fail, you keep trying. So you have failure, failure, failure. And once you have a win, a success, that's when you stop. So what type of distribution do you think describes the number of rounds you play? A geometric distribution. So we have a sequence of Bernoulli trials, and we have a sequence of failures that end in a success. So each round is a success or failure. That's the Bernoulli part. And each round is independent of one another, and you keep playing until you encounter the first success. Now, this is an example, in addition, of why distributions exist. When you study them, right? We talked about, for the geometric, we talked about the interviewing problem, right? But this could equally apply to this idea of you keep flipping until you get the guess right. It's a sequence of failures that end in a success. Okay? All right. So we have a Bernoulli distribution for each of the trials, right? Now, Bernoulli crops up again and again, right? Bernoulli crops up in binomial, as was said before. It pops up in geometric, and it's also going to pop up in something called a negative binomial, right? And we'll talk about negative binomial hopefully in today's class meeting. So the second point describing the number of rounds, that's a geometric distribution, right? And the geometric is a series of Bernoulli trials, but not just any Bernoulli trial, failures that end in a success. Okay, so, all right, good. So one question you might ask, because of course, certainly each time you play a subsequent round, your wager doubles. So one thing that you might be interested in is on average, probabilistic average, how many rounds do you play? Because you need to know, gosh, can I afford the wager for a given round as the round proceeds in time? So that's a perfectly reasonable question that someone deciding if they're going to play this game might employ to make a decision. Okay. So we have a geometric distribution, and notationally, when you say some random variable, of course, you use a capital alphabetic character like capital X, and this little tilde here connotes the word is distributed as. So we have a random variable X that's distributed as a geometric distribution, and that geo, you'll notice, has a parameter here, P, and that's the probability of success. So whenever you see in the literature, not necessarily in the book, but in the literature, and you go off and you look up these different distributions, you'll see notation like that. X is distributed as a geometric distribution, right? So if we have some variable distributed as a geometric distribution from before, we said that the expectation, right, of that variable is 1 over p, where p is the probability of success. So if we had a 1/8 probability of success, then you'd expect on average, you'd have to play this game for 8 rounds, right? Because 1/8, 1 over that is 8. Okay. Any questions about this? Make sense? So another question that someone would reasonably want to ask, what is the desired profit amount? So for each round, the profit or the amount of money you get for a particular round, it doubles. So you might want to talk not just in terms of the number of rounds, you might want to actually have an actual dollar value associated with how much you can expect to earn. No, absolutely, of course, it depends on how much you wager, right? But let's do this mathematically instead of intuitively. Okay. So mathematically, what we have is this idea of a successive doubling. On each round, you have first 1, which is like saying 2 to the 0. On round number 1, you double it, which is like multiplying by 2. On the next round, you quadruple it, which is like multiplying by 4. And so this successive doubling on each round, you can model that as just raising 2 to the power, where the power is just the round number minus 1. So if we were to do that out here on the board with the schematic that I have up, right, the round number is, let's call round is x. And so if we said 2 to the x minus 1, 2 to the x, well, x is 1, that would be 2 to the 0, which would be 1. 2 to the x minus 1. So in that case, x is 2. 2 minus 1 is 1, so that's 2 to the 1. That's 2. Likewise here, 2 to the x minus 1. If x is 3, that's 3 minus 1. That's 2 to the 2, which is equal to 4. So we can absolutely model this successive doubling as just taking the round number, right, the xth round or the ith round, subtracting 1 and just exponentiating 2 to that result. Okay, so we have this successive doubling. And for the example I'd given, well, uh, it was 100, but you can use whatever number. It could be 200, could be 1,000, could be a penny. It doesn't matter what it is. But we have this desired profit. So now, if we were to describe what I'll call the money function, and that money function describes how much you're going to wager on a particular round, we take the desired amount, 100, the initial wager, and we multiply that by this 2 raised to the power of the round number minus 1. Okay? And so if you try that out, our money function, let's call that y. On the first round, that would be 100 times 2 to the 1 minus 1, which is 2 to the 0. That would just be 100. On the second round, that would be 100 times 2 to the 2 minus 1 power. That's 100 times 2. That would be 200. Likewise, that would be 100 times 2 to the 3, the round number minus 1. That's 2 to the 2. That's times 4. That would be 400, and so forth, right? And so this y function, we can call our money function to give it a name. We can use that to describe the amount of the wager for each of the rounds. Okay. Any questions about this so far? Make sense? So now, if we wanted to know how much money can we expect to make, we're computing an expectation, but it's not the expectation of the round number, it's the expectation of the money function. Okay? And so when you compute an expectation, it's not just for the random variable. You can compute that expectation for any function that you can compute over that random variable. Okay? All right. So this idea first, any questions about this? Does that make sense? Yes. Absolutely. Absolutely. But the amount you're wagering is still defined by that money function. And so at the end of the day, and you're absolutely correct, but at the end of the day, you don't know how many rounds the person is going to continue because, once you lose 800, you're like, okay, 3,200, right? At some point, someone's going to kind of think twice about whether or not he or she wants to continue wagering. And so you're absolutely right. But we did that intuitively, and we didn't do that mathematically. Okay. But in real terms, some people, depending on, you know, um, well, I'll just say it now. This is a demonstration of the idea behind value versus utility, right? Utility says how um, important is the outcome to the amount you're willing to put at risk, right? And so at some point, let's say if you said you're going to wager $20, right? Person might say, yeah, that would stink to lose $20, but it wouldn't break me, right? Then once you get to 40, and then 80, then 100, then at some point, everybody hits a value where it's like, you know what? I'm just going to cut my losses because the amount that I could win while the value is positive, uh, to me, it's not as important because I'm not willing to risk that much on that particular round, right? And so that's what the problem really talks about in this thing called the St. Petersburg paradox. But nonetheless, you're absolutely right. If you stuck it out to the end until you eventually win, then absolutely you're ahead. But let's say if this probability of being successful is really, really small, like it's 5% or 2%, the smaller that probability, the more rounds you're going to play. So at some point, you're going to be up to tens of thousands. And then you have to ask yourself, gosh, well, is it worth tens of thousands of dollars at risk just to get back my $200 to be up 200? Is it worth it to me? And that's an illustration of utility versus value. So you're absolutely right. If you play until you win, you definitely get it back. But then the question is, if if you went to a casino and they had this exact game, then yeah, it would be worth it sticking out to the end. But at the end of the day, you don't know if they're going to do that. You'd have to ask them what the parameters are ahead of time. Okay. Any more questions? No? So this expectation, the expected money function, talks about the expected dollars that gets put out, but not necessarily how much you're up, because how much you're up implies that you're going to stick around till you get that single win, that single success. Okay, so now that we have a money function that talks about how much we wager on each round, um, let's talk about the expectation of this thing. Okay, so the expectation, like any expectation of some variable, now instead of saying e of x, I should say the expectation of some function of x, because this is just some function of our x, which is the number of rounds. So this money function is this 100 times 2 exponentiated to the round number minus 1, right? That's a function of the round number. Now here, it's not the expectation of the rounds, it's an expectation of this money function, okay? And so when you compute an expectation, it can be an expectation of the random variable or any function of the random variable. And when you compute the expectation of a function of a random variable, you're talking about the probabilistic average of the outcome of that function, okay? All right, any other questions? Questions? So let's take a look. And now this doesn't work. We're having a total equipment failure here today. Let me go to the keyboard then. So if we take that expression for the expectation, see if that, nope, all right, now it does work. Maybe the batteries need jiggling. We can look at this expression and we notice here that our 100 here and P, they don't involve X anywhere. X is the index of this summation. And so for all intents and purposes, they look like constants. And so using the distributive rule of multiplication over addition, we can factor out what is common, which is the 100 and the P for each term under this summation. So let's do that. So we do that and we have a leading 100 times P. And now we have this 2 to the x minus 1 power, and we have this 1 minus p quantity to the x minus 1 power. We make the observation that the 2 and the 1 minus p have the same exponent. They're both exponentiated. So we can join them together, essentially taking advantage of, you could call it distribution of multiplication over exponentiation. They're both exponentiated. So we're going to do and it's the same amount of exponent. So we're going to do the multiplication first and then the exponentiation second. Okay? All right. So this distributive law works for multiplication over addition, but other other operations as well. And if you think about it differently, another way to think about it is that when you have something raised to a power, you're multiplying it by itself some number of times. So this 2 to the x minus 1 power is like saying multiply 2 times itself, 2 times 2 times 2, x minus 1 many times. Likewise, this 1 minus p to the x minus 1 power is like saying multiply quantity 1 minus p by itself, x minus 1 many times. So if you have a long train of 2 times 2 times 2 times 2 and a long train of 1 minus p times 1 minus p times 1 minus p, you can associate them so that you have 1, 2 multiplied with 1 minus p, and then you have another 2 multiplied with another 1 minus p, right? So you can think of that even as associative, reassociating the multiplications. So what we can do then is now we can write 2 times quantity 1 minus p, and both of those are exponentiated to the x minus 1 power, right? So you can either multiply after multiplying by itself, or you can multiply those two terms together and then exponentiate x minus 1 with that x minus 1. Does that make sense? Okay. Excuse me. So now we have this term, and so we've collected both the 2 and the 1 minus p underneath that exponentiation by x minus 1. So, okay, and this is in the book, and I don't agree with what the book says. It has, I think, a typo. So I'll correct that typo on the board here, and that's what I wanted the pen for. So if we look at this expression, we have that leading 1 minus p, okay, and that's a constant. And then we have this infinite sum here. Now we multiply 2 times 1 minus p. And so that p-value, it's the probability of success, and it can take on values as a probability between 0 and 1 on the real number line. But something happens, something interesting happens when p is less than equal to 1/2, or p is greater than 1/2. So when p is less than equal to 1/2, well, this whole expression is infinite because that's an infinite sum. And let me explain why. So we have inside of the summation, we have 2 times 1 minus p exponentiated to the x minus 1 power, regardless of what this x is. Okay. So if p is less than equal to 1/2, let's see what happens when p is exactly equal to 1/2. When p is exactly equal to 1/2, so for p exactly equal to 1/2, this expression 1 minus p is precisely equal to 1/2 because 1 minus a half is a half. And then 2 times a half, when I multiply by this 2, right, that just gives me a 1. So that's the same as saying 1 to the x minus 1 power, and I add it to itself an infinite number of times, right? Well, that's infinity, right? Because 1 to any power is still 1. So that's the same as saying take 1 and add it to itself an infinite number of times, which is infinity. So this entire expression where p equals 1/2, that's now infinite. Okay, so let's take the example where p is less than 1/2, because that's less than equal to. So let's take the p less than 1/2 part of that less than equal to. So if p is less than 1/2, right? 1 minus something that's less than 1/2 is going to be greater than 1/2, right? Because 1 minus a half is equal to a half. If 1 minus something smaller than a half, it's going to be greater than a half. Does that make sense? Questions? So if you have something that's greater than 1/2, this expression, and you multiply 2 by something that's greater than 1/2, well, 2 times something that's greater than 1/2 is greater than 1, right? And so if you have something like 1.02, right? Or 1 point something, right? If you have some quantity that's greater than 1 and you multiply it by itself some number of times, x minus 1, each time you multiply by something greater than 1, that value is going to increase, right? So for example, if you have 100, and that's how compounding interest works, and you said, I'm going to multiply that by 1.05, on the next round, you have 105. right? And then if I multiply again, I'm going to add another 5% to this value. So multiplying this value 2 by something that's more than a half, you're going to have something that's going to be greater than 1 when you do this multiplication by 2. So if you have something that's greater than 1 and you exponentiate it to the x minus 1, this is only going to grow in size. So you have something that's big. Now, something that's big, if you add it to itself an infinite number of times, it's going to be infinite, right? Any number greater than 1 added to itself infinite number of times is going to be infinite. So for both of those cases where p is equal to a half and p is less than a half, that result for the expectation is going to be infinite. Okay? Any questions about this? All right. So let's take a look at the other case. Now, this is where I have an issue with what's in the book. And I'm going to change slides here and kind of blank a few things out and do that computation. So we have 100p times the infinite sum, x goes from 1 to infinity, of 2 times quantity 1 minus p exponentiated to the x minus 1 power. Okay, so what happens when p is greater than a half? So let's take that scenario. So if p is greater than 1/2, that's the other case. What we did before was p is equal to a half and p is less than a half. If p is greater than a half, well, that means this quantity is going to be less than 1/2, right? Because if you take 1 and you subtract something bigger than a half, what's left is less than a half. And you could even try that out yourself. All right, well, if 1 minus p is uh, less than 1/2, right? Okay, so you take something that's less than a half and you multiply by 2, what you're left with is something that's less than 1, right? So we take our 1 minus p, which we know is going to be less than a half because we're subtracting greater than a half from 1. If I multiply both sides of equality by 2, you get 2 times 1 minus p is less than 1, right? Because 2 in the numerator, 2 in the denominator, they cancel. So if we take something that's less than half, multiply by 2, we get something that's less than 1. So if you have some value, let's call that value r. So this whole value, we're going to call that r. And it just so happens that r is less than 1, right? Because 2 times something less than a half is less than 1, right? So we have something r, and it's exponentiated to the x minus 1 power, and it just happens that r is less than 1. Well, what happens when you take something that's less than 1 and you exponentiate it? You multiply it by itself. It gets smaller and smaller and smaller. An example that we've shown is that if r is equal to 0.1 and you multiply it by itself, r squared is equal to 0.01, r cubed multiplied by 0.1 again, 0.001. And if you keep multiplying, it gets smaller and smaller and smaller. The decimal place where that 1 is gets further and further out to the right. Okay? So already that's a small number, r to the x minus 1 power. And now we're taking that and we're summing in an infinite series. Well, that's exactly a geometric series, right? When this exponent is 0, it's a 1. When the exponent is 1, when this exponent is 0, we get r to the 0, which is 1, and we get r to the 1, r to the 2, and so forth. We're adding them together. So that's exactly a geometric series, but we have this weird thing here. The bottom index here for the summation is 1 when it should be 0. But we can fix that up with a change of variable. Does that make sense? So we talked about before for a geometric series that if we have a sequence, and let me erase this, and that sequence says sum for for I goes from 0 to infinity of a to the I, where a is less than 1, that result is equal to 1 over 1 minus a, right? That's what we showed last time with the geometric series. this is an equivalent expression for that infinite sum. Okay, so what we're going to do is we're going to remove this confounding x equals 1. So we're going to say let uh, k equal x minus 1. Okay, we're just going to make that substitution. And if we make that substitution, we write an x minus, every time where we see x minus 1, we write k. Likewise, if we have x here is equal to 1, well, if k is x minus 1, k is equal to 0. So k goes from 0. Now, if x is infinity, infinity minus 1 is just infinity, right? So we write the upper bound here is infinity. And now we have r. K is a substitution, r to the k power. Now that looks like the right form for being able to replace it with a geometric sequence, what that closed form solution was that we had from before. So now we take this sequence and we can rewrite that as 1 over 1 minus r. So remember, we said we know this value, 2 times 1 minus p, we know that's less than 1, so we just called it r, right? And so what we do, we replace this r with 1 over 2 times 1 minus p, right? 1 minus, oh, there we go. Confusing me. There we go. And that's our result, right? So that's the problem I have with the book. They're not making proper use of the geometric series when they write that solution. Okay, it's over there. So we have this expression, and this expression is infinite for cases where the probability of success in this game is less than equal to 1/2, and it's equal to this closed form expression, 100p upon 1 minus 2 times 1 minus p quantity if p is greater than 1/2. And so this is an interesting quantity because essentially this is infinite for part of the time, right? And for half of the cases for p, it's going to be an infinite expectation. So even though the random variable is finite, right, the amount of money on each round, the function of that random variable, even though it's finite, the expectation is infinite, right? So it's this paradox in probability called St. Petersburg. And the fix for this is beyond the scope of this class, but you can just, at this level, think of it as an illustration of the difference between value, which is what expectation gives you, and utility, if it's reasonable or how valuable that particular outcome is to you. And so if you think about it, let's say P was very, very small. You're going to have to play many more rounds in order to get back your original money. But then as the rounds go higher and higher and higher, you're going to have to put at risk a larger amount of money. And so this is something from economics, and utility theory has tools for how you evaluate what the right decision is. Do I play or do I give up? Do I stop playing? And it shouldn't be based on value because of this paradox. Because if it's on value, you're going to keep going. But then at the end of the day, you might run out of money to put at risk. And so is the risk, is the risk worth the reward, of the long-term reward? And companies play those gambles all the time. If you think about it, should I build this factory? Should I hire X number of new employees? Should I buy this facility? Should I open a plant in this location? And so forth, right? And so this utility computation is another way of evaluating such problems, because just going on the value alone doesn't tell you if the decision should be made from one round to the next. Okay? All right. Any questions about this? Does that make sense? All right. And this is in the book. And please note, I will repost the slides. There's a problem with how they do that in the book. In the book, they do it this way, and that denominator doesn't make sense based on the geometric series. Okay? All right. Any questions about this? No? Make sense? All right. So let me do a time check since we lost time due to the pen. Okay. All right, so let's take a look at another related distribution. And all these distributions, they're Bernoulli the binomial and the geometric and this game have something in common, is that they use the Bernoulli distribution, the Bernoulli trial in particular. So negative binomial is related. It makes use of the Bernoulli and it makes use of geometric. So let's take a look at what the negative uh, binomial does. Now remember, this is negative binomial, which is different from binomial. For a binomial, you had a sequence of successes and failures, and what you were measuring with the probability is the probability that an n number of trials, so n plays of some coin flipping game, that the probability that you'd have x many of these be heads, right? So you're counting the number of heads in a string of n outcomes, right? Each one of which can be heads or tails or two-way. No, with the negative, bless you, binomial, with a negative binomial, what you're measuring is a sequence of independent Bernoulli trials. So you have n many trials, and along here in the schematic, along the bottom, I have trial number 1, trial number 2, trial number 3, and so forth, up to and including trial number n. So each one of these trials is a Bernoulli trial. So you have a two-way outcome, and each one is independent from the other. So you could call that flipping a coin, asking someone, do you want chocolate ice cream or vanilla ice cream? Any two-way outcome can be modeled as such. So each trial can have a success or failure outcome, and there's a probability associated with success. Likewise, you could say that probability is associated with failure, and by law of total probability, come up with the probability of the other outcome. So nonetheless, we have a success and failure for each trial, and what we're after with the negative binomial is the number of trials you need to obtain k successes. So in the regular binomial, you could call it the regular binomial, you have n trials and you're looking for the probability of a certain number of successes. Here, you're looking for the number of trials to get a prescribed number of successes, k many of them. Does that make sense? So there is a distinction. Binomial, you're talking about the probability of a certain number of successes in n trials. Here, you're talking about the number of trials to get k successes. Okay? All right. So here we have n trials. And let's say the number of successes, we'll call it x many successes. You have the first success, the second success, the third success, up and including the xth success. So you have x many successes. So you have a number of trials, and there's some trial at which you get your kth success. And that trial, we're going to call it the x trial number x. Let me revise that. It's not the x success, it's the trial. So there's some trial at which once you execute that trial, you flip the coin, you're going to get that last and kth success. So what we want to know is, which trial is this? We're calling it trial X, but on that trial, you get the kth success. So that means a couple of things. That means on all the trials before that, you have k minus 1 successes, right? On all the trials after that, that means, well, you don't really care, but it means you don't have any successes, okay? So here you have some first success in this part of your sequence of trials. And then on this xth trial, aha, you get your kth success. Okay? All right. So let's work from this. First, any questions about that? Does that make sense, the schematic? Okay. So remember, you're counting which trial gives you your kth success. Okay. So if we identify the trials before the xth trial, well, that's x minus 1. So we have the first trial up into including the trial just before it is trial number x minus 1, right? So if on the xth trial you have your kth success, that means somewhere between trial 1 or within trial 1 through trial x minus 1, you're going to have k minus 1 successes. Because the only reason to get the kth success here is that you must have had k minus 1 successes interspersed somewhere within trial 1 through trial x minus 1, right? Okay, so that being said, well, how many successes are scattered among these trials? Well, k minus 1. If on trial X you get the kth success, you must have had k minus 1 successes some point before that. No, it doesn't mean that you had all k minus 1 right up to, trial success number k minus 1 was on trial X minus 1. That doesn't mean that. What it means is that somewhere here, you might have had k minus 1 successes very early and then had all failures, and all of a sudden you had your kth success, right? All that means is that scattered in between trial number 1 and trial number x minus 1 are k minus 1 successes. Okay, that's really, really important. So does the order matter for these k minus 1 successes? Let me ask you, does it matter, the order? That one success came in the first position, another one came in the third position. Does it matter where these k minus 1 successes occur? It does not. It does not. Absolutely does not. What matters is you had k minus 1 successes somewhere. So no, it doesn't. Okay. So let's say our rate of success, our probability of success is p, and it doesn't matter what p is. It's the same p that governs the Bernoulli trial or the Bernoulli distribution. So if p is the rate of success, well, by law of total probability, what is the rate of failure? It's 1 minus p. Okay. So we have the rate of failure is 1 minus p if the rate of success is p, probability. So using that, if we were to look at what happens in the first uh, positions up to and including trial number x, well, we have some number of failures, right, in those first x trials, and then we have some number of successes. We just don't know where they are, right? We do know absolutely that we have one success absolutely in position for trial x, right? We know that. And we know that we have case minus 1 successes someplace else. We know that. So we can model probabilistically without knowing position yet that we have k successes, and each success is at a rate of probability p. So we have probability p times p times p times p k many times, once for each of those k many successes. And then the remaining x minus k are failures, right? By definition, if you have k successes in x trials, then that means x minus k of those trials are going to be failures, each one at a rate of 1 minus p. So we write 1 minus p, the probability of failure, multiplied by itself, x minus k many times. Okay? All right. Does that make sense? Any questions about that? But yes. Mhm. Yes. Mhm. Yes. Ah, we'll talk about that. So if the number of successes in the number of trials for one success, right? If it's trial number 1, then you can't have 2 successes in one trial because the one success, that's the number of trials in which to get k successes, right? And so if the number of successes is greater than the number of trials, that's physically impossible to do. So if I said, how many trials do I need to get 2 successes? Well, you need at least 2 trials to get 2 successes, right? You can't do 2 successes in one trial. Okay? Does that answer your question? All right. Any other questions? All right. So this is our basic probability, but we haven't yet addressed the ordering that we talked about. It has to end in a success. So here we have different ways of getting those case successes. But what we're talking about here is all of those orderings that we can have of the k minus 1 successes preceding that trial number x. So we account for that by counting all the different arrangements we can have of k minus 1 successes in each of these x minus 1 trials, because it's assumed that last success occurs, that k success occurs in trial number x. Okay? So we use combination, and we say x minus 1 trials choose all possible arrangements of k minus 1 successes. So we're choosing k minus 1 things out of x minus 1 choices, right? X minus 1 positions. And that accounts for the many different orderings that we can have of the k minus 1 successes before we get to that last trial x where we have the singular success, that final kth success. Any questions about this? Does that make sense? Okay. All right, so this is called the negative binomial distribution, and this is the probability mass function of the binomial distribution. What it says is P of x, and this is the functional form. It's x minus 1 choose k minus 1 times 1 minus p quantity exponentiated to the x minus k. So those are all the failures, the 1 minus p's, and p times p to the k power, those are all the successes. And then this leading coefficient, x minus 1 choose k minus 1, are all the arrangements of the k minus 1 uh, successes that you have in the first x minus 1 trials. Okay, so this is the probability that the xth trial results in the kth success. Or you could say the probability that you have k minus 1 successes in the first x minus 1 trials, and then the last trial is a success. Okay? So it shares some similarity with the first. Any questions about this? All right. So it shares some similarity with the geometric distribution. And we're going to use that similarity to talk about the expectation and the variance of the negative binomial distribution. So if you think about what happens, here we have a sequence of k many geometric distributions. Because remember, a geometric distribution was a sequence of failures ending in a success. So starting at trial number 1 for this negative binomial, we're going to try flipping the coin, flipping the coin, flipping the coin. And it's going to become a failure. So we'll get failure, 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 and then success somewhere. Okay, so that's our first success in that sequence of k successes. Then we're going to take another coin and we're going to flip that coin, flip that coin, flip that coin. We're going to get failure, 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 success. That's the second success in the sequence of k successes. And then we're going to do it again and again and again. And essentially, what we have, each of those k many successes, the last and kth of which we got at trial x, looks like the singular success in a sequence of k many geometric distributions. So essentially, a negative binomial is a back-to-back sequence of geometric distributions. We have failure, 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 success, failure, 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 success, failure, success, failure, 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 success. And we do that k many times to constitute our k many successes. And you're counting the total number of trials over all of those geometric distributions. Does that make sense? Question? So essentially, the negative binomial is just a sequence of geometric distributions where the geometric distributions are just sequences of Bernoulli distributions where those Bernoullis are failures that end in a success. Okay? So as a sequence of geometric distributions, we have k of them in that sequence of geometric distributions. So using this properties of linearity of expectation and linearity of variance, if we compute the expectation of a negative binomial, so we would note that as random variable x is distributed as negative binomial k, where you're looking at the number of successes k, and p is the probability of success, and there's our mass function here. I won't say that again, but the expectation of a single geometric distribution is 1 over p. And so if we have k many of them, that's k times 1 over p, or k upon p. And for the variance, it was 1 minus p over p squared for a geometric distribution. Since we have k of them, it's k times 1 minus p over p squared. Okay? And so knowing the relationship between these standard distributions is going to be really important as it pertains to problem solving. And so we're building machinery, and this machinery will help us in our simulations that we're going to have a bunch of them coming in the coming weeks so that you can analyze a scenario, choose the correct distribution, simulate it, and then use that simulation to answer questions. So that's what we're after. But we first have to develop the machinery that talks about the distributions, their properties, and the relationships between these distributions. Okay, all right. Any questions about this? Make sense? So please do go back over it. The book is very, very terse, not very many words. Some places they do a better job than others, but certainly there's lots and lots of information. This material is hundreds of years old, lots of information on YouTube and other places online. And please, if the book does not resonate with you, find something that does, because there's something out there for everyone. Okay, so with that, we'll end here and we'll pick back up on Tuesday with more families of distributions, the Poisson, and hopefully the screencast between my tablet and my laptop will work so I can have use of the pen to actually do that variance proof for the geometric distribution. So I will see you all on Tuesday. Please look out for another assignment tonight for this class. I think operating systems I did already. Yeah, I did already. So I'll be posting something for this class. All right, I'll see you Tuesday.